This video is going to be about histone modification, a part of a new up-and-coming branch of science called epigenetics, which is the study of altering gene expression without actually affecting the DNA itself. Alright, let's get down to business. Throughout your high school biology career, you probably learned a little about your A's, G's, T's, and C's, and how they're all wrapped up around these little beads called histones. And that's about it. Poor histones never get mentioned again. But there's more to histones than meets the eye in a high school biology book. See, histones are made of an octamer of 4 core histone proteins, arranged kind of like this, 2 of each. H2A, H2B, H3, H4. What? Where's H1 though? Oh, there it is. H1 isn't technically a core histone, it's a linear histone. It's found alone a little bit down the DNA, and it helps stabilize the DNA. But most of the fun epigenetic stuff happens to the core histones, so we'll be referring to them for the rest of the video. These histone proteins are positively charged, and DNA is negatively charged. This causes an electrostatic attraction between the two, which is why DNA can wrap so tightly around histones. Each of these histone proteins has a little tail that sticks out called an N-terminus tail. These are the areas where the histone modifications typically occur. Histones are modified through the addition of different chemical groups to different amino acids on these tails. Although there are others, the most common are acetylation, phosphorylation, and methylation. Histone acetylation usually acts on positively charged histone residues, like lysines and arginines, on the N-terminus tail. Acetylation neutralizes the positive charge of the histone, thereby decreasing the attraction between it and the DNA. This loosens the DNA's grip on the histone, leaving it open for enzymes involved in transcription to express that DNA. This loose, transcriptionally active DNA is called euchromatin. Histone phosphorylation does the opposite of acetylation. It tightens the DNA's grip on the histone, packing the chromatin more tightly. It packs it so tightly, actually, that the enzymes needed for DNA transcription can't even squeeze in there and do their thing, making the DNA transcriptionally inactive. So those genes aren't expressed and are turned off. This type of transcriptionally inactive DNA is called heterochromatin. Histone methylation isn't as straightforward as other modifications. The effect it has, whether it loosens or tightens the DNA, making it transcriptionally active or inactive, depends on how many methyl groups are added and to which residues. These histone modifications, and epigenetics in general, have a much bigger impact than previously thought before. Why can genetically identical twins turn out so different? How do cells age? What is a new technique that we can try to cure cancer? All of these questions can be answered with epigenetics and histone modifications. This topic has huge implications for the future, so I'm glad you sat down and learned a little about it with me today. Thank you!